Kia ora and welcome to video 7 in the series Insightful Integration. In this question, we are going to look at a pretty tricky problem. We've got two vertical tangents there drawn on either sides of a circle. And we've also got a horizontal chord that divides into three regions there. So the question, in fact, is a differentiation problem, because if we read it, it says we're trying to minimize the shaded area. However, because we're minimizing an area, and I guess area falls under the integration standard, it's technically an integration problem. However, do reflect on the regions that you've got before you jump straight into integrals, because you might find that there's an easier way. And as always, give the problem a crack and then have a look at the solution after the intro music. All the best. Okay, this problem is probably the hardest in the series so far. There's a couple of ways to approach it. The idea is that we're sliding this horizontal chord up and down. We're asking what height here should we draw that horizontal chord so that the area is minimized. So first up, let's find the area. If we find the area using integration, and then that expression is going to be in terms of k, and then we differentiate it with respect to k to find the minimum, we'd set the derivative equal to 0. So that's the general gist of it. But I tried it the first time round with that k as my variable, my independent variable, and it wasn't so nice. So I've decided to, with this solution, make that my independent variable, because if we move the chord up and down, theta is going to change as well. And the reason I've done that is it makes the expressions for all the areas a bit easier, and therefore I don't have to use integration. Okay, because all I've got is a sector. If I think about this thing here, I've got a sector minus a triangle, gives me the area up the top, which is a segment, and then I've got a rectangle minus two sectors. So if I find the area of the sector here, a piece of a pie, and the other sector, same area, based on symmetry, and also the triangle, sorry, I don't think I said that before. If I also work this triangle out, so that Mag's colours, sorry for everyone else if I offended you there. If I did, just put it in the comments. And alrighty, so the total area is made up of the side areas and the top area. So first up, we've got the side areas. The side areas is the rectangle minus the two sectors minus the triangle. And we can find those areas in terms of the angle theta. The rectangle has a height of sine theta using trigonometry, and it has a base of 2 because it's the diameter of the semicircle, so 2 sine theta. The sectors, or the area of the sectors there, it's theta over 2 pi. There's 2 of them, by the way. It's 2 theta over 2 pi, which is the fraction of the full circle. Remember that 2 pi is 360 degrees, times by the area of a full circle of radius 1, which would be pi times 1 squared, and then minus the triangle. The triangle has an area of half AB sine C. Half A and B are both 1, so half times 1 times sine of this angle here, which we'll say call alpha, but alpha is just equal to pi minus 2 theta. Remember that pi is 180 degrees. So that's our expression for those areas, and it simplifies a little bit. 2 sine theta
The two sectors, the pi's cancel, the 2's cancel, so we're left with just minus theta. And the sine of pi minus 2 theta is just the sine of 2 theta. So no integration needed, just standard level 2 trigonometry. NCA level 2 that is. Okay, and then the top area. The top area is the big sector with the angle alpha minus the triangle. So it's alpha being pi minus 2 theta all over 2 pi times pi r squared, but again the radius is 1, minus the area of the triangle, which was a half sine 2 theta. And this dude simplifies, we're just got to be careful of how we do it. We've got pi over 2 minus theta minus a half sine 2 theta. Okay, now we need to add those expressions together. The side area and the top area is the total area that we're asked to minimize. So if we add those two things together, we get pi over 2 minus 2 theta, that pi over 2 sine theta, and minus 2 lots of a half sine 2 theta, so sine 2 theta. Okay, now we want to minimize this area, so we're going to set the derivative to equal 0. Derivative with respect to theta, the pi over 2 disappears, we get minus 2 plus 2 cos theta. So this is in an integration series, because you could use integration to find the area between a circle and a line. And if you did that, good on you. It's very similar to the last video in the series where we looked at how to find the area between a circle and a hyperbola. But this is just a different approach of doing it, because the expressions come out really nice. We don't have to use any ugly antiderivatives. And then the last thing we need to differentiate is the sine 2 theta, so it's minus 2 cos 2 theta, and we make that equal to 0. And that's the beauty of scholarship, right? The scholarship problems are across all areas of the curriculum, so something that might look like an integration problem could possibly be solved using other maths. Okay, to solve this equal to 0, we're going to need to tidy up the expressions, because actually what we've got here is a quadratic. We can replace this cos 2 theta using the double angle formula for cosine. Cos 2 theta is 2 cos squared theta minus 1. So if I replace that part of the expression, now we can see there's a quadratic equation in cosine. Minus 4 cos squared theta plus 2 minus 2 cancels, brilliant, plus 2 cos theta equals 0. Recognize here that cos theta doesn't equal 0, because cos theta equals 0 when theta is pi over 2 or 3 pi over 2. Now theta can't be pi over 2, that would make that 90 degree angle here 90 degrees, and that's not sensible. So we can rule that out as a possibility. In other words, we can cancel the cosines, or divide the whole thing through by cosine. And now we're left with 4 cos theta must equal 2. Cos theta equals a half. And if cos theta equals a half, we now need to find the height, because the question asks us, what height does the horizontal chord minimize? And that was the thing I was calling k before, is actually sine of theta. And I've just worked out what cos of theta is. So I draw a little triangle. It's a terrible start. Draw a triangle like that. That's not much better. Angle theta. If cos theta is 1 over 2, that doesn't tell you that this is 1 and this is 2. It might be 2 and 4 or 3 and 6, but it's that ratio. And it doesn't matter. We don't need to find the specific sides, and we don't need to find the specific angle. We need the ratio. So this number here will be the square root of 3, and therefore sine theta is equal to root 3 over 2, which is the height of the chord. That minimises the area shown. Awesome. Catch you in the next one.